Right, so this is Octave. It's pretty close to MATLAB. And so I have 0 to 1. And then I have this change of basis right here.
Okay, so if xc is 0,
when xc is 0.
So you're going from 0. I think you want the opposite of that, right?
Could be.
Because are you going to do integration? Are your integration points going to be in the domain -1 to 1?
Yeah.
So what you want to do is if I plug in -1 for xc, then you should get back 0. You're going the opposite direction. So just solve for x in this, so you have x is equal to 2xc minus 1. So when xc is -1, right, then x is -3. That doesn't really make any sense, right? It's the right mapping, but going in the wrong direction.
Okay.
So where you see, so in your code,
swap c out. Well, so just change this to x and this one to xc, right?
Yeah, and then solve for x. So change that to xc equal to 2x minus 1, and then solve for x. And then you'll get the right mapping.
Okay.
I believe. xc plus 1 divided by 2. Yeah, that's right. xc plus 1 divided by 2. So when xc is -1. Yep.
Awesome.
Okay, so that's your first problem. So and we call that the geometry, right? Because it's saying you have a parametric domain from -1 to 1. And then the geometry, the actual domain where you're computing things, we call the geometry or the physical domain. That's going to be 0 to 1 in this case.
Okay.
Okay.
And then I have, so this is the power basis.
Okay, and the power basis should be in the xc. You're computing these in the parametric domain.
Okay.
Not the x domain, xc domain. So you're computing them. You're going to evaluate the power basis at all of the xc values of the quadrature rule that you've chosen.
Okay.
So if you have 3-point quadrature, you'll have like a -xc value 0 and then a plus xc value on between -1 and 1, and then you'll evaluate your power basis polynomials at each of those values, and then that's what you're going to use for your computation.
Okay.
Okay, so those are 2 things that you fixed.
So currently I'm having it evaluate a lot of points.
Well, if you want to plot, then that's good. Like if you want to plot a curve, then you can just do a bunch of equally spaced points. But remember, to evaluate the integral, the points are quadrature points specifically. So you're going to have a loop over quadrature points like I have in my notes. Have you looked in the notes where I've got like the pseudo code?
I have looked at it before. The first time I looked at it was at the beginning of the semester. It didn't make much sense. And then I haven't looked at it since, but
let's pull it up. Go ahead and pull it up on your end. And so you go to topic 3.
Opening it up right now. Okay. So this one right here. No?
Yeah, topic 3. Going down. There it is. So this is basically the pseudocode for what you're going to be implementing. So if you start at the top, you're going to compute your quadrature points and weights, right? And those you just hard code in based on the notes.
Okay.
And then write a little routine where you see how compute mass matrix, that routine has a couple of subroutines, compute basis and compute geom. So you're going to want to define compute basis first, and you're going to pass it a polynomial degree n and an xc value between -1 and 1, and you're going to evaluate the basis there and return an array. N's an array, and it contains all of the basis functions evaluated at that quadrature point.
Isn't n p minus 1 in this case, because your mass matrix is n by n? So it's not exactly the polynomial degree?
Let's see. So the mass matrix is n by n. Yeah, so you'll be degree n minus 1. That's right.
Right.
So that's an error. So that should be n minus 1. I'll fix that. Thanks, Caleb.
Okay.
Yeah, let me fix that right now while I've...
Is there a reason that you're not just doing the mass matrix of size n+1?
Yeah, that might be an even easier way to fix it. In any case, I'm going to fix it. So we got n
minus n+1.
Yeah. Yeah, just give me just a second here.
So I think I compute a mass matrix and a force F matrix. And I compute a solution that fits the graph I get.
Okay, that's surprising since clearly your geometry is wrong.
So see this, I have it fitting the curve.
That's pretty good, huh?
Mm-hmm.
I think you've consistently switched x and c so that it still gives you the right answer even though they're in the wrong place.
Yeah, it's on the wrong domain. Yeah, I understand. Okay, but okay, good. That means you're doing 95% of it right.
95. That's good.
Yeah. Yeah, so let's go back to the code that we were looking at on my lectures. So refresh and you'll see the new, I updated it.
Ah, yes.
Okay, so right, so you want to focus on writing the subroutines first. Compute quadrature points, compute quadrature weights, compute basis, and compute geom. Those 4 routines you write separate.
Okay.
And the geom, compute geom, what is the geometry in this case? This is just your map, right, that we just talked about. It's your map that's going from xc into x. Because x is your physical coordinates, and so that mapping is what we call the geometric mapping. So
okay, so it's not the sine function, it's just
the mapping. Yep, it's just your domain. It's giving you information about the spatial domain where you're solving your problem. So specifically, you pass in a Gauss point in the parametric domain between -1 and 1, and it computes the corresponding x value, right? You just plug in xc, it returns an x, and then you also get dx dxc, which in this case will just be a constant value because it's a linear map, it's a linear function. Later, we'll make that more sophisticated, this compute geom. Right now, we'll just assume it's always linear.
okay. So in this case, dxc would be either a half or 2.
Yeah, it's going to be a half because your map is going to be x is equal to, let's see, xc plus 1 over 2, I believe, right? So when xc is -1, then it's 0, and when xc is 1, it's 1. Yeah.
Okay.
So the rate of change of x with respect to xc is going to be a half, and that makes sense because your interval -1 to 1 is length 2, and you're mapping into an interval that's length 1. So the rate of change should be 1/2. Okay, and then once you have those 4 routines, it's almost literally this code verbatim, right? Like, depending on which language, you might have to change some of the, you know, some of the semantics a little bit, but otherwise it's this.
Awesome. So I think I have this code, at least a functional thing that does this,
Yep,
but I just need to fix these guys.
yep. And then
And then, yeah, the other bases are, let's see, yeah, the Bezier one,
yep.
Bernstein.
Yeah. Let me take over the screen share here, and then I can explain and write at the same time.
That would be awesome.
Okay, so let's go to, where are we? Yeah, so depending on which polynomial basis, they're defined over like specific domains, right? Like the power basis is easy over any domain. Legendre is conveniently defined over -1 to 1, so you don't have to do anything there. Chebyshev also is -1 to 1, so you're good there. Do I even ask you to do Chebyshev? I don't remember.
No,
I think I
no.
just asked you to do the Legendre. Lagrange also is -1 to 1. So Bernstein is the only one where you have to map it. This definition here is over 0 to 1. And then I give you the equation to map it to any domain right here.
Okay.
So if you can put -1 for xc0 and 1 for xc1 and plug it in here, you'll get the polynomials in -1 to 1.
So I didn't understand the notation n over I.
Okay, so this is n choose I.
Mhm.
So let me,
I was trying to code it, and since I didn't understand it, the program was saying, "Why are you putting negative things in there?" So
yeah, so it's called a binomial coefficient, and this is it right here. I should probably add that to the notes. That's a good point. If you have that question, then everybody will. So yeah, so everywhere you see that notation, it's called the binomial coefficient, and the way that it's actually computed is right here.
okay.
Yeah. Okay, other questions?
I think that's it for me. I guess I was stuck on number 4, but that was like 2 weeks ago, and I haven't looked at it yet. So by now, since we covered so much stuff, I'm sure I'll be able to clean up my code. You remember mine was doing the crazy graphs. So
Oh yeah, yep. And I updated this and cleaned it up so that everything is actually a norm here. So I put some absolute value signs. So every error term now is a norm, which is kind of what you want. And then, so it should clean it up a little bit. It doesn't, if you've already done it, don't change anything. But if you haven't done it yet, then this will be a little easier to do.
awesome.
Dr. Scott, just while we're still on the Bernstein polynomials, I'm just having a little bit of trouble understanding how to code equation 14, where you use the C1 and 0.
Okay. This one right here?
Yeah, I'm just having trouble understanding how to code in those two values and just understanding what they are.
Okay, let's do a couple of them. Let's see. So let's say we want to do n equal to 1. So there's going to be two polynomials because this is linears, right? So I is going to go from, let's see where I, yeah, so if n is equal, so if you have n things, then I is going to go from either 0 to n or 1 to n plus 1, right? So let's just, so if I do the linears, let's say I choose n equal to 1, then b0 is equal to 1, 0. And then xc1 is going to be 1 minus xc. xc1, so that's 1 minus 1, so that's 2. And then n minus I is what? It's 1. xc minus 1, so that's plus 1 over 2 to the 0. So then this is equal to 1 choose 0 is what? If we go to this guy here, it's just going to be 1, but let's just, so 1 factorial over 0. So 0 factorial is what?
1.
1. And then 1. So it's just 1, right, for this guy. Okay. All right, so then this guy is, this is 1.
So how did you get the C1 is 1 and the C0 is -1?
Because that's the domain we want to, that's where we're going to do integration. So we've just chose that to be our domain.
That makes sense.
Okay, and then this is to the 0th power, so this is 1. So our first Bernstein polynomial, B0, is just 1 minus 6c over 2. And then we do B1 the same way, right? You plug in I equal to 1 and do the same thing. And what I would do is probably just hard code, like maybe up through cubic polynomials or quartic polynomials into your code. You just work them out and type them in. Did that address your question?
Yeah, so that makes sense with having just the bounds. But I guess just a question with that, why not just do a for loop to do everything above our 0th polynomial?
That's exactly what you can do.
Okay, cool. That's kind of what I've done.
Yep.
Okay, that helps a lot. So it's just so we can hard code in 1 and -1 for the C1 and C0.
Yeah, because that's where we've chosen to do our Gauss quadrature.
Right.
So that's a good domain to choose.
Right. Okay, let me just make a note of that. Okay, perfect. And then if it's all right, if I can ask another question about the Lagrange basis. That's the one I'm having trouble trying to code a little bit right now. I think I might be on something that might work, but I don't know. It's just the Lagrange basis is just a little bit tricky for me to kind of wrap my head around how to code this in an efficient manner.
Okay, so if you want some, so you know what this symbol means, right? The product.
Right, it's basically a sum, but with multiplication.
Yep. So you're going to have a loop. You're going to have a loop, right, from 0 to n. Let's call that m. So we're looping over CI. So you're gonna have a loop is gonna take the place of this product. And then this product ranges over what? Zero to n,
0 to n. Mhm.
right? And then you'll have a little if statement in here that filters this out, right?
Oh, okay.
If, so what is this, for
So if m equals
m,
I
m
equals 1.
equals 0 to n, and then if m doesn't equal, let's see, I, which is what you're going to pass in I, right?
Mm-hmm.
Then you go in here and you evaluate this thing here. And then there'll be another loop. So this will give you one polynomial. This will give you the ith polynomial. And then you can have another loop on I out here that will compute all of them.
Okay. Okay, that makes a lot more sense. Just
Yeah.
that if statement helps.
Mm-hmm.
Do you have any tips on how to, because kind of what I'm doing right now is I have those 2 for loops, and I just put in that if statement. Do you have any tips on how to multiply all of those parts together? Is there a
Yeah,
function
yeah.
that does that?
Yeah, so this basically is an accumulation, right? So
Mm-hmm.
what I would do is I'd have some variable, let's say, you'll have some variable, let's call it L, and you'll set it equal to 1. And then in here, you'll compute some temporary, which will be equal to the term that you're working on.
Right.
And then you'll go L times equals the temporary,
Times equals.
which is just L is equal to L times the temporary. And then you just build L up. It starts out at 1 and you just keep multiplying onto it as
Okay.
you go through the. Yeah, so you just, yeah, so it's just, you're just basically kind of accumulating by multiplying over and over again. So you need a temporary that you evaluate the current term, and then you need some running variable that you're multiplying into over and over again.
Okay, and so that L times temp would be inside the for loop, including the from
It would be
that's
inside the
m
if
from 0
statement.
to n.
Yeah, it would be in here,
Okay.
right? Because for each of these m's, you're evaluating one of these terms. So you evaluate one of these terms, put it into temp,
Mm-hmm.
and then you go ahead and multiply it into your running L, which is the whole product.
Right. Okay, awesome. Yeah, that really cleared it up for me. I think I can do that from there.
I have a few questions, Dr. Scott.
Okay.
So for the Bernstein basis that we're just really looking at, you mentioned that you could like kind of define what the Bernstein polynomials are over any closed interval.
Mhm.
Can you define like a new Lagrange basis for any closed interval as well, or is it only over -1 to 1? And that same
Oh
question
yeah,
applies
you
for
can
like
do a change of
Legendre.
variables on any polynomial. Yeah, any polynomial, you can do it. You know, let's say you have a function f of xc, and then you just say that, well, I want xc to be equal to some g of like eta. You can always do that, right? You just plug f of g of eta, and then everywhere you see xc, you plug in g of eta and just reevaluate the whole thing.
Right.
Yep.
So in general, or like, how should I say this? But the reason I guess why we want to like reevaluate over like a different interval is because in like the parametric domain when we're doing our flex modeling, we have like each of those like I guess elements or I
Yeah.
guess subsections, and so then when we map those back to the physical domain using the defined like Bezier extraction that it maps to like the specific thing that we want it to.
Mm-hmm.
Okay.
Yep. Yeah, I mean, change of coordinates is like all over the place, right? Because you're just, the other option is you move the quadrature points into whatever domain is most convenient for the polynomial basis. That's also a possibility. But I think it's easier just to do everything in one domain. Just pick one, whatever, -1 to 1, and then just map all the polynomials down into there and then evaluate them. And the geometry will just be that linear, and then you'll be done.
Yep. Thank you.
Yep. Okay, who else is on? There are some students that are
Oh, Dr. Scott, sorry, one last question on the Lagrange basis.
Sure.
With these, we have the Cassis of 0, kind of these arbitrary Cassis from 0 to n.
Yes,
Is that
yes.
just something we're going to feed into our functions for the
So
bases?
you can pick any value that you want, but I would just pick equally spaced points. So
Equally
for the
spaced points.
for the quadratics, just pick these points.
Okay.
For the cubics, you just pick these points. Right? Just pick.
Okay, so that's a simple thing you can just hard code
Yeah.
in.
Yeah.
Perfect.
Yeah.
Awesome. Thank you.
So let's see. Tyler, do you have any questions?
I think I don't really have any specific questions per se. Most of what I'm working on is just the coming up with the algorithms. I just have had very little experience with any sort of finite element software. So it's mostly trying to teach myself how to learn like the basics of those software just because I'm very inexperienced with any of them. So
you're doing what now? You're running software?
or just the trying to learn I've been trying to learn MATLAB. Trying to figure out how to do the algorithms in there.
Oh, you mean like learning how to write the algorithms inside of a
Yeah.
particular language like MATLAB?
Yeah, I'm just not familiar with any of these languages. So I feel like I'm just going a little bit slower with with coming up with these algorithms just because I'm not super familiar with the
Okay.
language.
Do you have any questions that we can help you speed up? If you're happy to help you. I mean, everybody starts from a different vantage point, so I don't mind that at all.
Mm-hmm.
Is there anything in particular that you'd like me to address?
I don't think I have anything particular right now. I think it's hopefully this next week I can spend some more time working on that and seeing if I can get the program or to code the algorithms in there. But for right now, I don't think that there's anything super specific that I have.
Okay. All right. Any other questions, comments, even at a higher level? Let's see. Okay, any questions about the concepts, like independent of the homework?
So, Dr. Scott, when you derived the weak form the other day, you started from the energy functional, right? But in general, I think we always have a strong form and then we can derive the weak form. And I guess only for conservative systems we have energy functional, and it's not always true that we can derive it from the energy functional, right? The weak form.
Yeah, the reason, yeah, you always can, you can just write down any weak form you want, really. The point is it may not make any sense, but you can always just string a whole bunch of integrals together.
Mhm.
So yeah, the weak form is a generic, kind of a generic way. And in fact, you know, people tailor algorithms by creating weak forms where they have terms in there that just are playing numerical, they're just for numerical purposes. Some of them are discrete, you know, there's all kinds of things that are done. The reason that I start in this class from an elastic strain energy is because then you know like what it is. Like I've done it the other way and students just don't have any idea. You just write down a weak form, they're like, well, what is that? Like the fact that you have some system that has energy and you're minimizing it, and that's what the weak form is,
Mhm.
I think is the appropriate mental model that you should always have.
Okay.
And so I want that to be the first way that they learn this.
Yeah, and I think that makes more sense than even coming from the strong forms sometimes, because you're like, what is this test function thing? And, you know.
Yeah, right. Exactly. Like, and here, the notion of a test function comes out naturally as the way that you define a directional derivative in this context, right? The test functions are like the vector directions that we're taking the integrals in. And so it just grounds the concepts. I've done it both ways, and the other way, no, especially engineering students who have a lot of background in strain energy, you know, displacements, stress, internal, external energy, like this is a much easier entry point than just a purely mathematical way of thinking about it.
Yeah, it definitely makes more sense when we derive it from the energy. Like it just comes naturally, the test function, and yeah.
Mm-hmm. Yeah, and a lot of, in structural mechanics, there are usually energies, right? It's common in structures. It's not as common in other fields. So, and then the idea that like, okay, we have an energy, and then the strong form is really just, from my perspective, the strong form is you're just telling yourself what equations you're solving. Rarely would you just write down a strong form. I can't even think of a strong form that, even if you see it as a strong form first, somebody got it through some kind of conservation, integral conservation law, right? Like they don't just come from nowhere, you know? So Carl, I'm curious about your perspective on all this. You're coming from a completely different vantage point. Do you have any comments on the course so far?
You know, though I almost commented on Canon saying, you know, learning to think in algorithms is a task in and of itself. And in my experience, in all those years of teaching that class, getting people to think algorithmically was one of the biggest steps they had to take. And don't focus too much on the language you're trying to do it in. Make sure you focus on what is the algorithm. And then don't be afraid to ask for help from people in the group to get it into the language.
Yeah. Yeah. I've had a similar experience teaching this course over the years. There's a kind of a challenge that comes when you have to turn something, a mathematical statement, into for loops and if statements, right? So
exactly.
Yeah, and when I took it, as soon as we started looking at each other's code, that really helped a lot. So really, if people have code and they want to put it up on the forum to look at or anything like that, I think that's a really helpful place to get to.
Yeah,
I
that's
mean,
great.
looking at the examples, I mean, even looking at what you've got there, that's great. You know, we don't really talk much about writing pseudocode anymore, but sometimes just trying to voice, what am I trying to do in English? Okay, now once I can voice that, let me now try to translate it into some computer language, whatever that language may be.
Mhm. Yeah, and the thing about this is that if you guys are able to get a code up and running, then the course will really take on a new life, because all of this is just, you know, words on a page until you can actually start computing and you see that it works. So in this next thing, this is like all the stuff that, this is an entire, this right here is the code for the flex method that we're discussing. It's still fairly simple and a lot of it's the same, but there are a few new concepts that are introduced. And so I would even recommend maybe writing the pseudocode in MATLAB or Python or Julia or whatever you're doing, and then working backwards and saying, okay, I've got this, now I got to fill in like this routine. Okay, what do I do here? You know, and the code will give you an like a mental framework that you're working in, and you'll start mapping the code to the actual equations, right? Because for some of you, this is just going to be a bunch of gibberish, right? Until you see what it actually is in code. Yeah. Okay, good. Well, I think if there's not any other questions, I think that I like the idea moving forward on Fridays. I think I will take an opportunity for everybody to show their code. So next Friday, I'd like for everybody to show their code, and I think that that's a good way to get everybody kind of off the ground here, because there's kind of this like, we got to get you up on your feet here, or else you're not going to get anything else out of the course. So let's work at making that happen. Does that sound like a reasonable plan?
Sounds good to me.
Okay, well, you guys have a great weekend, and I'll talk to you on Monday.
Thank you.
Thank you.